in 1973. So Lorenz asked the question, can a butterfly in Brazil cause a tornado in Texas? And this question is really the question that initialized the concept of butterfly effect. That is, a small perturbation can cause a huge change later on in a chaotic dynamical system. That's also the question that more or less made the field of chaotic dynamics a big thing pursued and studied by many people. The original tool used by Lorenz to answer this question, to ask this question and then answer the question, is the Lorenz system. The Lorenz system is a model constructed by Edward Lorenz to model atmosphere convection. It's a very simple model in the sense that it models a periodic arrangement of convection cells. And he did a Fourier series truncation so that each cell, the velocity and the temperature distribution of each cell is represented by just one single Fourier, one single term in the Fourier series. So after this truncation, the whole system has been reduced to 3 variables, all evolving as a function of time. X, the circulation, and the horizontal and the vertical temperature in equilibrium, right? And the equilibrium is essentially just the first term in the Fourier series. So the system can be derived into a very simple set of equations called the Lorenz system. And if you go to Wikipedia or anywhere, you can find the simple formulas you can use to evolve the systems. And what I want to show you is the butterfly effect of that is demonstrated by this simple 3 degrees of freedom ordinary differential equation. So what you're going to see in the next screen is a collection of solutions represented in just the x-axis and z-axis. And the collection of systems evolve from a set of equations that differs only slightly in the initial condition. Okay, so essentially it is representing if a butterfly has perturbed the system, has flapped its wing, right, causing a tiny perturbation, maybe 10 to the minus 9 or something perturbation to the system. And we're going to observe how that small perturbation is going to evolve in time. So what you see is a collection of systems identified by the color, which is really just representing the different initial conditions. What you're seeing is that the collection of solutions initially was close to each other. However, the nonlinearity of the butterfly effect it really makes very close initial conditions diverge after a finite amount of time. And as you see now, even colors that are very close to each other, let's say yellow, right? That means initial conditions that are very close to each other initially has been spread to very different parts of the phase space, or the x and z coordinate space. What that means is that a small perturbation initially could cause a huge difference in the state of the dynamical system later on. So this is the famous butterfly effect. In using this simple system, Lorenz has answered the question that yes, a butterfly can cause a tornado in Texas. Of course, the conclusion has been duplicated in some much more sophisticated weather and climate models. So this is actually a climate model, and what you see is the difference in the mean sea level pressure between 2 perturbed simulations. And the perturbation is very small in magnitude, such that after 4 days, the amount of difference you see, right, is about 60 pascals. Now, after 15 days, the difference has magnified, if you look at the color bar, for 10 times. And this is really a demonstration of this butterfly effect. A small perturbation initially is going to cause a bigger and bigger difference in the weather patterns as the days goes on. And after 31 days, the magnitude has of the difference has magnified to thousands of pascals. So this is the positive answer that a butterfly in Brazil can cause a tornado in Texas. And this phenomenon is observed not only in weather and climate, but in all kinds of chaotic systems.